The Zeeman effect is potentially caused by the oscillation of particles within a magnetic field through levels of energy density. This being the initial state, which would align with the center or transition state, and so should remain the brightest as the majority of photons will be released there. The other state being the low state, being of lower energy as the energy density is reduced there, and the high state as the energy density is increased there. This differential in energy density is caused by the fundamentals of what a magnetic field is and leads to the oscillation of particles being sent out from the magnetic source. The fundamentals of a magnetic field are also the likely cause of the repulsion of a flame or high energy particles in a gaseous state. Heat and therefore energy is affected by the magnetic field as the field creates a state of low energy. This is naturally less conducive to the high energy particle, and so the energy is quickly lost as it enters. Particles that avoid the magnetic field are not affected, and so they continue as expected. This results in a seeming repulsion effect, but is not quite the case. The flame is not pressed down so much as the energy is pulled in and reduced a lot at a faster rate by the magnetic flow, leading to a smaller flame. Particles will avoid this low energy state if possible, as lower energy is less attractive on the gravitational level. Different polarization of the spectral lines resulting in different appearances of the spectral lines may be more evidence towards the nature of particle motion within a magnetic field. Okay, so what am I saying here? Basically, when you look at atoms, right, they have certain spectral lines, right? Like points at which they release photons at. There's different energy levels, right? And basically, when inside of a magnetic field, instead of it being a solid line, it kind of spreads out, right? And so what is being shown in these different images is they put like a polarizer up to these different to the light, or like to these spectral lines, and what they noticed, I don't know if I could really do it justice here. I can't really, I can zoom in. What they noticed is that, I'm doing my best here. Sorry, it's not focusing well. But you can see that in this one, right, it's got like just one thin line, but in this one it's got two distinct lines on the in the opposite area. And so what I'm trying to say in this video, in this video, what I was saying before is that because this is from what's polarized, we can get a better understanding of the direction or the motion of these photons when they're being sent out of the electron, right? When the electron is releasing these photons, right, we can get a better idea of the overall motion of either the electron itself or, I guess the relative, like the photons. And so pretty much, I think what I'm trying to say is that it's the electrons. You can observe the electrons' motion themselves in this, because you have a center beam where a majority of the light is getting sent out at, right? And so when not in a magnetic field, there is no magnetic waves. And since there's no magnetic waves, right, all of the electrons are releasing their photons within the same relative range, right? And they're sending them off in every direction. It's whatever. But when you put it in a magnetic field, then the electrons are kind of being affected by these magnetic waves. And as I've said, these magnetic waves are basically particle motion upscaled, right? These tiny particles are causing an overall waving motion in, the particle fluid. It's not that there's nothing there. It's that there's like small particles that are creating this back and forth flow and this back and forth is causing points of higher and lower energy. And so these photons are being released at either the transition state, which is in the middle, or at the edge of its limits, right? It's like, oh, okay, this is the point of lower energy because it's closer to the magnetic source, and closer to the magnetic source, it hits its limit, right? Of, lowest energy. And then, when it's at its farthest, when it's farther away, it's at its, higher energy because it's farther away from the magnetic field. So that's the higher side, right? But on each side of these, the motion of the electron is basically, it's kind of like hitting like an endpoint. So it's like, boom, right? It's like slamming against like a wall, right? Back and forth, boom, hit the wall, boom, hit the wall, right? Back and forth. And so its motion is different than when it's in its transition state. So at this point, like on the two ends, the electron is in the process of turning around, right? Basically, in theory. I think that's what I'm trying to say here. Is in the process of turning around, but when it's in the transition state, which is the middle point, it's releasing photons while it's just in constant motion, right? So the photons can go wherever. And so those photons will be released in a different way than the ones when it's being turned around, right? So basically what I'm saying is the reason why when you polarize it, you get either the one way you will look at it, you polarize it and you observe basically the two lines, and then you turn it the other way and you only see the one line, is because of the motion of the electron when these photons are being released. And the reason why the electrons are moving in this fashion is because they are moving with the waves of the magnetic field, which is caused by the motion of the smaller particles and the reduction of overall energy. Because instead of all the energy being evenly dispersed in a magnetic field, it gets jostled around, because basically the magnetic field is pushing away, basically it pulls in, the process of a magnetic field is it creates a point of very low energy, and because it has a point of very low energy, it creates a flow of particles that are, kind of sucked into this point of low energy. And this sucking in of particles causes an effect on, that particle motion ripples out and affects everything else, right? And with distance, this is lessened, right? Because, energy dissipates basically and other things. But when you're close to the source, there's a lot of particle motion happening, and because there's so much particle motion, there is a lot of energy being absorbed. But since it's in a cycle, the energy is not replenishing, it's just staying absorbed. And because of this, particles try and move away from this point, and when they do that, they bunch up, but then they're like, oh crap, now we're bunched up. So then they unbunch, but then they move towards where there's no energy again, and then they go, there's no energy here, and then they move back, and we get this wave. Basically, we've got a wave generator, right? Like a magnet is a wave generator, basically. And so you end up with this energy being created, but it's not energy that is directly useful to us. But we can convert that energy with generators and stuff, and that's why magnets are such a big part of everything. On like power generation and electronics and stuff. Yeah, I think what I'm trying to get across there is that the Zeeman effect highlights the fact that there is, while we think that the motion of electrons is random, it's not entirely random. And I don't remember what this study was talking about, or like what the overall proof of this video was and what they were trying to say with it, but that's what I took away from the information that they collected and the data that they had, is that basically electron motion is not entirely unpredictable. And the motion of particles in general is not entirely unpredictable. There are certain things that we can account for, and I don't know, I think it's interesting. So yeah, I think that's all. Peace out.